Let's not forget the sponsors. They help as part of the organisers to make this thing run. Better Building was our corporate conference partner. Design Builder, you'll see there, stand up, gold sponsor. IES, another gold sponsor. Oricon, company we came from, sponsored some keynotes, and Tiana, our industry partners as well. So remember I said before a few people couldn't be here face to face. Unfortunately, our next speaker couldn't make the journey all the way. I think he's in Copenhagen, so it'd be nice. It's really early in the morning. But I'd like to introduce to you online, hopefully he's here, Professor Dr. Zoltan Nagy, and he's going to speak to us about occupant-centric approaches to improve energy performance. Zoltan.
Thank you, Quentin. I'm in the Netherlands, but it is still cold. Let me share my screen and see. I've been redoing my slides after Jen's presentation, so let's see how much I could work into that. There we go, continue, and we should be good to go. If you don't see my slides, please holler. Other than that, well, so thanks for having me. I'm really sorry I couldn't make it. Life happens, and this is where we are. But what we'll talk about, my main message, I tried to adapt my presentation a little bit for this remote format, just so that it's a little bit more interesting. I threw in a couple of memes, which my daughter said I'm not using the correct way, so you can correct me on that. And I changed the message a little bit to something a lot simpler, which is that everything is connected. And then while this is a building simulation conference and the title is building performance simulation, we should be thinking a lot more what happens around the boundaries of buildings when we go up or when we go down. So when we talk about many more buildings that impact our built environment, or when we go into the occupant scale, how that impacts how buildings are performing. And really there's one message today: everything is connected. And what I will do is I'll talk about two big projects, or two main projects through our last 10 years of work in my lab, that kind of try to illustrate this and try to kind of motivate even how to explore further this sort of research. And some of the motivation, you see that picture, not motivation, but really just illustration, because nature has figured this out. I don't know if you go through a forest, you see a bunch of trees, but what we don't realize, a lot of these trees are connected on the ground with fungi, and they communicate information between each other. They can share carbon, they can communicate if there's predators coming on, they can share water, they can, when in terms of droughts. So really trees are not isolated individuals in the forest, but they are connected and communicating and then living together. And so, when we think then for our buildings, the question is where we are in our buildings, and then most often a lot of our papers that we write are like, oh, this building has saved 20% energy, but it turns out when we do our fancy optimizations, actually things can get worse, and I'll come to that second comment a little bit later. Maybe we do something when all the buildings would do the same thing at the same time, that we cause an issue on another end, in this case grid. And so as the third point here kind of like illustrates, it would be actually better if we had some sort of autonomous behavior that would happen without us having to do a lot of work, because it's very complicated to coordinate a lot of buildings. But nonetheless, the combined effect will impact our larger built environment. And the last point is sort of like just as sort of like not a jokey vision, but a visionary statement, is like, okay, the buildings are not isolated anymore. We understand this slowly but steadily, and they impact big, many areas, starting from climate change to whatnot. And so the question is, how can it be part? And Le Corbusier named it the machine still living in. And so that's kind of like where we're going back with all the technology and with everything being connected, is that we're actually living in a machine and living in a robot in some sense. And so this Corbusier's arc is coming back to haunt us in that sense. But so before we get there, and then I'll show you where we are on this sort of meme slide, a little bit of my background to see why I'm talking about crazy things the way I do is because I have a background that is also not very linear. I started out as mechanical engineer, and I started building robots in my PhD, micro robots actually. I don't know if you can see the scale, but this white line here, it signifies 1 millimeter. So that's really small. It was supposed to be like an eye surgery type robot that you would inject in your eye. And so that was my PhD work and trying to do magnetic fields on that. Really fascinating work, but really small and really fast. So micrometer scale, like the thickness of those robots, 50 microns, the width of a hair. By the end of this talk, we'll be talking about cities and decades and centuries. And so you see how that 15 years spans from millimeters to, city scale structures. It's kind of insane when I look back at it, how this transformation happened, but it's fun journey to be on and to continue. These pictures that I put on, these are my postdoc project, a gateway from mechanical engineering into architecture and architectural engineering and construction. These facade elements that we invented and designed and put together, they were supposed to mitigate light and generate electricity and provide shading and provide visual aesthetics to the building, but also visual integration with the occupants on the other side. When I left, we were, before these pictures, this picture was taken or this rendering was taken, the biggest question really that I had with my background coming from robots and coming from a mechanical was, well, how do we control these things? Like there's so many, some of these architect renderings are crazy, 100 modules, 200 modules. We need something that, does not rely on too many detailed computation, too many detailed simulation. We need something simple and so on. But then pretty soon after, we realized, well, this is not a lot different, just a metaphor for a city block. Each of those modules might as well be a single building, and they do something. And then coercively, again, together, they do have an aesthetic, they do have a show something. And just like that, all the buildings on a city block or multiple city blocks together have, in my world now, some sort of energy demand that is related and that can be coordinated or not, and it can look into total chaos, just like if these panels do anything completely chaotic, or it can be orchestrated in a smart way so that the outcome is something that we want and it's useful. And so that's kind of like the journey that began when I moved to the University of Texas. And the first thing we did was, well, can we actually try and build a software where we could simulate hundreds of buildings and how they interact with each other, with their environment, and how can we sort of control them, or study the control rather than study the design. And so we looked around, and it was really hard to run 100 energy plus simulation models in parallel and do the control on top of that. So we scratched that. And so rewrote from scratch this piece of software they call CityLearn, where we could do that. And so over the past 10 years, mainly two PhD students, Jose Cantelli, the two bottom names there, and then Kingsley and Wei in the last 4 or 5 years, really put together an impressive piece of software that allows us just to do that. And at the end of the day, the challenging part for me was to communicate that. So adding that to the previous presenter, to get it out into the world so that this work, this was really fun that they worked on, is not lost and has been used. And so we were fortunate enough to be able to do that. I don't know how it happened, but it's really cool. Many people, I counted about 100 plus papers that we were not involved in over the past couple of years. We organized hackathons where people could use the software, so it's easy. We spent a lot of time actually making it useful, which is not very common in academic settings because nobody pays you for that, which is a shame because it's useful. And so, what I want to do now is kind of show you what we can understand now because we have this kind of software, and then how we can extend that and think about where we can go further. Since this is a building performance simulation conference, I thought this would be quite fitting. So the first thing, or one of the big questions that comes up in this sort of like connected scheme, or how the buildings are connected, is can we actually take what we learn on one building and just put it on another building, and thereby save a lot of time and a lot of money, and speed up learning process, speed up optimization processes. So that's a very abstract question. In the context of energy flexibility, the question is, can we actually learn a flexible energy strategy that this building could perform? And why we want to do that, just a quick background, is because we want to integrate way more renewables into the grid. This is the challenge everywhere, whether it's Australia, the US, this is the California duck curve, or in Europe. We have a lot of solar during the day. We have nothing in the night. We have a lot of demand, especially residential in the night when the sun goes away. And so then the ramping up causes instabilities on the grid. And so what we want the flexible behavior for is that we shift our demand from when we don't have electricity, renewables energy, but we need demand. And so we need some kind of buffer. And so what we did together with EPRI, the Electric Power Research Institute, we used their data from this case study in Southern California of 17 or so single-family homes, super efficient by US standards, like 10 years ago. And what we tried to see is all these homes had solar panels and battery storage, so home battery storage. And we had smart meter data, so we knew exactly how they were performing. And so we could simulate and estimate the battery control in these buildings. And so what we tried to do is we compare what their engineers have done, which is what they call the time of use based control. So basically when the electricity was cheap, you would charge your battery during the day, and then in the evening, you would discharge it. And then we wanted to do something more fancy. We used the reinforcement learning approach, which is a technical term, and I won't go too much into detail. If you're interested, we put out a nice summary last year. The main idea is that you don't have to know a lot about the building, but your agent kind of like understands what's happening through interaction, and then it can optimize its behavior throughout the operation. And one of the drawbacks, in fact, is that it might need a lot of data. So what we could show, what we could show is here you see four typical buildings, typical building data on the left. The black curve is your typical demand, which is without control. And then the red dotted lines are basically what these time of use controllers do, which is to charge during the day and then discharge during the night. And you see it's the same for every building. This is four. I just blew them up so you can see them better. And then the green ones are the sort of more refined, more adapted AI controllers that we use. But what was interesting is, like I said, the drawback of these controllers is typically that they need a lot of time to learn. Somebody published a paper said these need 15 years of data to be optimal. And I was like, yeah, okay, but we don't need optimal. We need good enough, for one. And second, that was a fake. That was not a good study. So what we tried here is do the opposite. We tried, well, what if you start a little bit and then you just optimize, and or you run a week and then you put whatever you learn to the next building. That was one way to speed up things incredibly fast, and it was really good, and then you would just be fine. And that was a really interesting finding that people just haven't seen before like that. So I think that was pretty cool. The other thing, and we're getting back to the connectivity thing. First of all, you see over there in all the buildings, and you see the black curves a little bit slightly different in every building. This is mainly occupant behavior because you've seen all these buildings are in the same block. They're all the same, built at the same time, built to very high standards for US standards. And so the differences are mainly how people use the buildings. It might be a different family. They might have different schedules. People might be retired or have families, and so they have children to go to work and things like that. And so you have different behaviors. And so the red controller, the time of use one, doesn't care about that. It's all the same thing. That's what the EPRI engineers have installed on those controllers. They all do the same thing. The green one is able to adapt to these differences. And so through these knowledge transfer between them, we're able to speed up quite a bit. Through the fact that we can adapt to them, we can actually improve upon the collective behavior, because if you add them up together, which is this curves here, you see that the red ones actually even amplify, and they have a higher peak than the previous peak. They have a higher peak here than the previous peak was here, which is not a good thing if you keep adding bigger and bigger peaks on your grid, even if it's solar. Whereas the other one, the green one, is a lot more smoother and a lot less peaky. And with that, what it means that without actually understanding and optimizing all the buildings together, but just by exchanging some of the information on how they behave and by adapting on the individualities, we can create a collective behavior that is useful for everybody without the complexity of optimizing the collective behavior. And that's actually really powerful. And so that brings us that we're now on that initial meme, the red dot is pretty much something that happened that we didn't want to do, but we didn't anticipate that would happen. But if we had done something like that collectively on hundreds, if not thousands of buildings, it would have very much happened. And so that's something we can prevent. Whereas the third point there, coordinating like starlings, which is without any sort of, main brain that makes these birds fly in these nice patterns, an emergent behavior has occurred, and we could optimize across scales without actually having to optimize computationally across scales. So that's actually really powerful because it allows us to scale. And because we see that occupant behavior has such a large impact, we haven't modeled it. We just saw it in the demand curves of these buildings. But then we started thinking, well, we should add that. And so with a group in Concordia, this is Mohammed Ouf's group and Catherine Casper's PhD, we implemented occupant behavior models and trying to see things like, well, if you start doing demand response and the people don't like it and they start to become uncomfortable and they start to override these decisions, and what happens. And so without going into detail, but you see different models at different curves and different scenarios, but you have different behaviors, of course. And so again, the power of this, the tool that we developed, is that now you can do this for hundreds of buildings with all kinds of different behaviors that you're interested in. And then you can see how the aggregate will happen and how that plays out down the road. So that's something, again, very fascinating. But then we thought, oh man, somebody else was like, well, this building stuff is fine, but we're actually interested in electric vehicles. Can we use your tool to study what happens when you charge cars and discharge cars? What happens to your buildings? We're like, well, we don't know. Why don't you try it? And so these guys in Portugal spent 2 years or so integrating electric vehicles into CityLearn. And then now it's pretty cool. So you can add where you're going, how far you've been, what your state of charge is, when the car comes back, and then try to use your car's vehicle, your car's battery for, meeting some of the loads of your building, which is again something that 10 years ago we were not thinking about, because a car was a car and a building was a building, but we're electrifying all the buildings and we're electrifying all the cars, and all of a sudden a car is just a battery in the building that is there sometimes and it's not there another time. And so all of a sudden it is a pretty big asset of the buildings. And so enabling to integrate it into your daily energy operations is actually quite important as we move forward, to understand the potentials and the impacts you will have if all of your neighbors plug in the electric vehicle at the exact same time, what that will do to your neighborhood distribution grid. And then I was giving you these examples, and I was showing you the example of 15 buildings, and then some of you might have thought, well, he's talking about hundreds of buildings, but he's showing us 15 buildings. So here's a study that just came out from Italy, Sabrina Savino and Alfonso Capozzoli's group. They studied a different algorithm where they coordinated building behavior, actually with a multi-agent deep reinforcement learning approach, and showed that can scale up to 100 buildings easily. And so with that, you can now think of coordinating, whole neighborhoods essentially to improve energy demand, to improve flexibility, and to basically become better stewards of the energy transition. So really, this is one big part, and this CityLearn has been going on for a long time, and it will keep going on for a long time. If you're interested, get in touch with me, please, because we're looking for more collaborators and more developers. It will move soon into like more of a foundation model, so that there's no one ownership, and it's more of a community-driven development, because this is very key to energy transition, and I think it should be free and open source for everybody to use, so that we're not stuck in behind paywalls and behind companies that don't want to share this information. So that's one part where everything is connected and one building is not, the same, or one building cannot be looked at in isolation. And so, but as we started looking at this and we're like, okay, so we can coordinate 100 buildings. And I said it, and we can reduce energy emissions. All of the examples I showed you, reduce emissions, reduce energy, you reduce the ramping on the grid, you reduce peak load, everything's awesome. But then you're like, okay, now we're looking at neighborhood scale and bigger neighborhoods, larger neighborhoods, half a city, and all of a sudden other things are important or also important. You're like, what about land use policy? How does the city develop? Like if you're looking at not just, this year, 2025, but what is in 2050? And like, oh yeah, sure, we just changed the weather file. And I was like, yeah, no, you don't just change the weather file. In 25 years, the city will look different and the buildings will have different impact on each other. And whatever you do today will have impact in 30 years. Oh, yeah. And then it occurred to me, obviously, the weather file, the climate change can happen on different versions. And then grid decarbonization happens at different scales and different rates and all other things, right? And transportation and things like that. So this is a whole other, everything is connected sort of thinking that hurt me in my brain quite a bit. And I was thinking about this quite a long time, how we can even approach this, because I'm somebody who's interested, as you can tell from my background, it's always, robots are mechanical, electrical, software, and then the architecture robots was also like that. So it's about integrating the different aspects, even if they're not perfect, but connecting them so that you can see how they interact. And so that we did here, this was about 5-6 years ago, we set out with a bunch of colleagues thinking about it. And the application for it is really that if you think about climate action does not happen on a global scale anyway. It doesn't happen on a national scale because it's too big, but it happens in local scales, in municipalities. But they don't have tools for do it, and they also have tools to sort of understand where things are going, especially when you make a decision today. Where will you be in 5 years or 10 years and 20 years with that decision? Over the last 2-3 years, we started seeing these digital twins and urban digital twins, and that's the kind of idea that we've had back then. The name wasn't around yet. The problem was, again, there's no tools to like get an idea of how things go when you just combine stuff. Like there were again a lot of tools. Some tools are like, okay, let's give us the net zero goal in 2050 and optimize back what the trajectory needs to be, how many PV panels we need to deploy, how many what kind of insulation we need to do, and that's kind of like optimize that. But that's sort of like an optimal pathway that will never occur. What we wanted to do is think about pathways that may occur and then show that you can actually be, on totally different pathways, and then you have decisions to make on which one you take. And you can read the paper that just came out a little bit earlier that summarizes it, but you can see it as like 20 people on it. And that's because we had people from urban planning, we had people from engineering, and we had people from public policy to sort of like integrate their knowledge into this sort of like connected database pathways project, which, it's really about sort of like data handling at the end, but connecting and the results are pretty cool. So let me show you the framework, and then just one brief example from the city of Austin. So the framework starts that we're actually looking at parcel level data, and we're trying to understand what is on that parcel. And then we did it for a few neighborhoods, but every parcel has buildings on it. Those buildings can develop into new buildings or from single family to multifamily homes. Parcels can merge. And we do that based on whether the land value changes and it's higher than the reconstruction value of the home. So that's the zoning policy. And then the urban planners develop policies for the city development. And then on the sort of like decision-making process of whether or not to adopt technologies, we had an agent-based model that thought about how the people in individual buildings on those parcels make a decision whether or not to add solar panels and batteries to the homes. And that's a whole completely different thing that I have no idea about, but people who knows about it that came up with a model and they can calculate it. And that's pretty cool because now we can combine the two things. So in this building, we have this house and there's this probability that, you know, there will be solar panels on it. And we do this for the whole neighborhood of, you know, X thousand buildings. And so we can start develop these scenarios, like I said, development scenarios like higher density, which is not North American, but low density, which is typical North American single family homes, technology adoptions, what will they do? Some exogenous variable like climate change, like that you cannot impact, but that you have, okay, let's say you should be able to impact, but let's assume we don't, and so we're on trajectories based on the IPCC scenarios, and all of those provide you energy demand for each of the parcels, for each of the decades that we're looking at in each of those development scenarios. And then the energy demand, we use the grid because it's all AC, because it's electric in the cooling climate, to convert into emissions, and then the grid mix can also evolve over time. And so as we move forward in time, it may or may not get cleaner. And then the end result is your annual emissions. And so that's kind of like the connections. You see in this framework, you can add easily things like transportation emissions or any other sort of things that you have because you go down all the way to individual parcels. So you can have individual people, but also aggregate for neighborhoods or cities, which makes it easy to scale. The examples from the case study you can see here, the high density scenario on the top where the lighter single family homes are displaced by the darker multifamily homes, unlikely to happen because Texas. And then the lower density, which is a more typical development where the single family homes stay, and then there's some development along the the arteries, the transportation arteries, the large streets with a lot of cars, then where the apartment buildings are placed. And then this is for every decade. I'm just showing you the 50 to 100 just to see how it transforms. And then each of the parcels have the buildings on, and for each of the buildings, we have an archetype that is then simulated according to the IPCC scenario that you're on and whether or not the energy that you have, the solar panels and the batteries that you have in your home. So you can see here a substantially different number of units, almost twice to 3 times if you have a high density scenario versus the other ones. You have a lot more people in that neighborhood to deal with. So population growth is kind of like how you deal with it. Here's the example for the climate change scenarios. Like I said, the IPCC, we looked at these 3. At that time, I thought we were on track for 2.5. Now I think it's more this one, but the results I'll show you after is for A1B. And then the grid decarbonization is really like we do nothing, and then a super aggressive one, net zero by 2050-ish, and then the in-between halfway through, just to have like a bandwidth of what we can look at. And then the policy incentivization was whether it's a policy that asks that you want to buy, that helps you buy PVs or not. And so that was also built into that. So you can see there's a lot of all the combinations, the 3 times 2 times 2 scenarios. And so you run all of those for every decade between 2020 and 2100. And then we look at a lot of graphs. And I'll just spare you it, but I'll give you just one graph that tries to summarize, because there were some interesting things that we could see on this one. First of all, in the beginning, so sort of like a legislative period, there's not a lot of difference. So whichever path you take, you will always end up in the same after 5 years, roughly speaking, with the error margins. There's no big deal. But after 100 years or 80 years in this case, you can see that you can end up, on average, assuming this is the average of some variation, 8 times different between scenario B and scenario F is a factor 8 or so in emissions per unit or emissions per capita. And that's substantial. So what decisions we take here, obviously you can make decisions after, but once you're on a path, it gets even harder and harder to go from one to the other one. So that's one message. So your pathways diverge in this particular case scenario, which is, I think it's scary, honestly, because I want to make sure that we're going down here rather than up here. The scary thing with the orange one and then the D one in particular, and these are just combinations, so you don't have to take care of in particular, of the particularities. But the scary thing to me when I saw these is that all of the curves go down. The F is the reference when you do nothing, so you can ignore that. But all of these curves go down up to, the next 30 years, which is like, oh, we're on a good trajectory because our brain is linear. And so if you only see the first part, your linear brain will be like, everything's fine. But the problem is that after that, some of these curves turn back up. And so that's because in the case of G, this is low density and no grid decarbonization, which is probably where Texas is heading. So you have efficiency gains because you build new buildings and all the go away. And so the new ones are more efficient. And so that's kind of like where you go down on this trajectory. But then eventually climate change happens. And so your demand starts growing. And if your grid is still dirty, your emissions will start growing. And so in this particular scenario, you end up where you started after 80 years. And that's really, really troubling if you look at it. Hopefully that's not going to happen, but this sort of rebound also happens down here, also for the other low density and moderate grid decarbonization to a little less extent. And so these rebound effects may happen in other places at different times and at different intensities. But what's important is that, again, we cannot look at this and say, well, my building saves this much energy, saves this much grid emissions, when in reality, we're all in this sort of bigger boat. And the building does not exist in isolation, but it exists in this policy setting. It exists within this neighborhood. And so whenever we do this work, that's sort of like the call to action to our communities. Whenever we do this work is we need to try to acknowledge how that fit into this larger picture of the energy transition, because otherwise it really might just be an artifact that doesn't do a lot. And I'll have to try to wrap up soon, but and I'm linking back now to the beginning. And so again, the really simple message is that things are connected, and what we want to do is acknowledge that in our work and make sure that we actually try to work with people across boundaries, because at the end of the day, we have a big problem, and we cannot silo us each other from that big problem because it doesn't care about our silos at all. And the thing that I learned by not being in the silo myself all the time, because just moving across all these different fields and disciplines, is that it's just fun to talk to people that have different backgrounds. And there it's really where it's such a cliche that innovation happens at the boundaries. But it, as I've shown you, it's really cool, and the communication between is really hard. What Jen said is when you have different backgrounds and you have different sort of like the same thing, but you have two different views on that same thing, and you try to work it out, and then something emerges which is different than the sum of the two parts. It's kind of like what makes this worthwhile. But at the same time, the problem is so big that being stuck in a silo is not going to serve us at all. And so you need to come out of, this is my building, and move into more, okay, here's how this fits into the larger scheme. And if you needed a personal motivation, the reason this slide scares me a lot, and those of you with little children, little grandchildren, is your children are born somewhere here. When they are your age, they'll be in the dark red. And so that work that we're doing today is going to impact their lives substantially more than what your parents has impacted your life in terms of climate impact. And so again, everything is connected, but now it's even on a personal level, right? So you're personally connecting your work towards the future of our species. So no pressure of the presentations that are coming up, but what we're doing here is saving the world to some extent. And so that's why we need to look at it in a much bigger picture than just that one building or just that one technology innovation. It happens everywhere, and we need to find the biggest levers in combination of these technologies that we're developing. So that's kind of like my spiel. So thanks for listening. I hope you enjoyed it a little bit. There's a lot of people I could thank, because obviously this didn't happen again on my own. There's a lot of people by name. Those are just the ones in my research group that I work with, but there's a lot of people in the audience, awesome people that I had the pleasure to work with that mentored me past 10, 15 years. And so hopefully we'll meet next time in person and you all get a high five and a fist bump. And for now, it's thank you, and have a discussion, or feel free to email me, and we can continue the conversation. Thank you.
Thank you, Zoltan. That was really interesting. We do actually have a few minutes for questions. I always have a few, but audience, we've got any questions out there in the audience? We've got a hopefully a roving mic, or you'll have to run up the back and talk. Any questions? While you're thinking and worrying about standing up and talking in front of a whole lot of people, Zoltan, if you were to sit in a design meeting with a client and they're about to, start thinking about either a building or a city, whatever scale you want to think at, what might be the first thing you might ask them and first piece of advice you might give to them starting on their journey on a new project?
Well, you bring the big guns. So my advantage as an academic is that I don't have to think about finance budgets, because the things we hear when I talk is like, oh, but we need to do what the client wants, and we need to stay within the budget. And I think the sort of, and I want to say this is what you have to do, but it would be nice if at some point the professionals would push back their clients and say, yes, this costs more, but at the end of the day, there's also climate challenge. And so, we want to do what's best overall, not just what's best for this particular project for the next quarter or the next 2 years. And I don't know how you get there. Honestly, this is not something I've thought about a lot, and it doesn't sound like it's something that's solvable easily just because of the way capitalism works. So my hope is more on rules and regulations, but that's also not a fun one to think about. I would like that actually somehow people adopt a mindset that we are more than just that building. We are a community, and our buildings impact everybody, whether it's, and not just our investors. I don't know, that's an idealistic view of things.
Yeah, I think you said something really interesting, which is where that innovation happens at the boundaries. Climate doesn't care. So I think the piece of advice someone else gave me a long time ago was to try and stay in the problem a little bit longer. Put aside some of the boundaries like budget, like program, and say, yeah, we know about that. Let's just stay in the problem a little bit longer. And it'd be interesting to see what comes out of that. And you're all here, a lot of you are simulation experts. You can predict the future. So actually start using those tools to help people understand the impacts of their decisions, because we're all very short-term thinkers, aren't we, sometimes? Was there another question out there? Yes, right at the back. Can a mic get to that person? There he comes. He's coming.
Hi, my name's Ryan. I'm from Neighbours, which is an Australian-based rating scheme in Australia. I was really interested about your analysis of time of use, particularly for low-scale building developments. In Neighbours, it typically is a commercial rating scheme, so focusing on commercial buildings. I'm just wondering whether your analysis looked into commercial buildings and also high density residential, and whether what the results were with time of use for those kinds of scenarios.
Yeah, you're right. So the examples I showed you were single family homes and residential buildings. We have not done other studies, but the problem is not fixed to residential. I've known other people have written about this phenomena that if you control on time of use, you will end up with a shifted peak, but in the peak nonetheless at a different time. So it's not limited to those areas. It's mainly because you optimize, whether it's an MPC or whatnot, or just the rules, that to do the same thing at the same time, and then there is no understanding that everybody else might do the same thing. That's the main problem, and it's not whether it's a commercial building or multifamily or single family. And it's the same idea. It's the same idea with which might be a little bit more easier to grasp, which is the EV problem. Like everybody has an EV, and everybody plugs it in at the exact same time and charges to charge it, then the whole block goes black. That's the same idea.
Well, thank you, Zoltan. That's fantastic. Sorry that we had to get you up so early and we couldn't see you in person, but I'm sure we'll see you soon. Just to finish off and thank you all. One note you might want to take away from you is perhaps we've got to design it better to start with. So let's thinking about, instead of necessarily looking at all the controls and mechanical systems, maybe we just design it better to start with. Something to take away. Well, I don't want to keep you. Now is time for some morning tea, a bit of time to rest, maybe get a bit of sunlight out there. Then after morning tea, we get into the first set of parallel sessions. So can I ask chair people to be in the room like 5 minutes before it starts, just so you know where to press the button. 11 a.m. we start sharp. People will be talking straight away, maybe doing a dance. And then for the rest of the day, we'll be moving around, but we'll be back here at 5:15 for someone smart to talk to you, and then we'll have some drinks at the end of the day. Thank you all. Go grab a coffee.